Okay, so I'm going to start now. So I'll start by revising what I have told you so far, starting from the first class. So the first thing that I told you, that large deviation, something called large deviation function, and it's very important. From one of the motivation is that this provides a possible generalization. Here? Here? Okay. So I've told you that there is something called large deviation function, and it is one of the reasons why it's important is because it provides a possible generalization of the concept of free energy, or rather the thermodynamic potential, to non-equilibrium systems. Now, then to introduce how to calculate this large deviation function, I started with a very simple example. That was this Langevin equation, which was a stochastic differential equation with this 1 degree of freedom, a system with 1 degree of freedom. And I had theta t sigma delta t minus t prime. And I looked at the system where there was a weak noise, and the weakness was parameterized by something, a small parameter epsilon. Okay. Then I derived two results of the large deviation. One was that if I'm in a potential, so that was f of q equal to minus del u del q. Then I showed you that in the stationary state, if I'm looking at the probability distribution of the position qf, it has a large deviation form in the epsilon small limit, and this goes as 1 over epsilon u of f minus u of qf minus u of q star, where q star was the position of the minima of this potential. Okay? So in order to derive that, I use this following action formulation. Or rather, you'd call this actually a variational formulation. Where the main idea was that if I look at the evolution of the trajectory, so q with time, okay, let's say starting at q star, I'm going at qf, in a time from 0 to t, then there is a path integral formulation where this probability qf given q star could be written as a path integral over two variables. So this is now in a Hamilton's formulation where I had an action. Okay. And then it turns out that there is a, if I look at a particular probability to see the position qf at time t, then there is one trajectory which dominates this probability, and that is obtained by minimizing this action. So at the end, my large deviation function, which I would call here as phi of qf, this is simply the S min over this P and Q. So at the end of the day, the calculation of this large deviation function, which is a stochastic problem, it reduces to solving this variational problem where I have to just minimize the action, and that's to find the least action paths. So another example that I talked about, where I looked at another type of observable, which was the area under the curve. So this is an observable which scales with time. Okay? So here I introduced that there is something called an additivity conjecture, which says that if I want to look at the least action path for this problem, it turns out that the least action path is time independent. And using that, one could very easily get this large deviation form for this quantity, which for the large time limit has this following large deviation form. Now, there was one clarification because after the lecture, many people asked me that could the additivity conjecture would work for this problem? No, answer is no, because usually the additivity conjecture would work for an observable which is scaling with time. Okay? Here the observable was not scaling with time. Also, the other point is that it may not work for all possible observables which is scaling with time. So every time you have to really check whether it works or not. There are many examples where it does not work. Okay? And so far, I don't know whether there is a necessary and sufficient kind of condition yet. Okay? So right now, the check is that you just look at consistency, do numerical simulations, or even just check. So at least I don't know if there is any other criteria. Okay, so all these discussions so far was to introduce to you, this is like a first step towards solving the many particle problem. Okay? So the basic concepts of this macroscopic fluctuation theory are already there in this one-dimensional single particle problem, single degree of freedom. Now what I'm going to do is to apply these techniques for systems with many degrees of freedom, where most of the interest lies for the non-equilibrium systems. You'll realize that the basic details are the same. The most details that the difficulties that comes are mostly the algebraic difficulties. Okay? So today I will talk about systems with many degrees of freedom. I'll start with a coarse-grained description, which is called fluctuating hydrodynamics. Then I'll show that in that, starting with that fluctuating hydrodynamics, one could write down similar action formulation. And again, you will find that the large deviation function of an observable in these kind of systems could be formulated into an action minimization problem. Okay? So that's what I'll do it today and also tomorrow in the last lecture. True. So the way I derived here, I still needed epsilon, but it's possible that you could start with a problem where you just first already rescale with the time, and probably there the time could play a large role. But I haven't done it, and I should check whether it really works or not. Okay? So for the observable, so this is for the problem where the observable scales with time. Right. Of course, so here, the time here in this form, the time played a big role. So one thing that I forgot is there was an epsilon for the problem we looked at. Okay? So you see, I could have formulated a large deviation form at the first part of the calculation without t being large, and it still had a large deviation form where I looked at qt 1 over epsilon. Okay? And there it was q of t. Okay? That we did at the first part of the problem. Then I said that if I now look at large t behavior, okay, then it turns out, then you can actually define this another form, which is like this, and there is a t comes out, and this becomes r. And the additivity conjecture works only in this large time limit. Okay? Because your optimal profiles, they first change with time, but it remains constant and first change. So only if you're looking at a very large time, then you can ignore these parts where it changed, and then the most contribution comes from the part where the profile remained constant. So here, R is not the optimal profile. R, I'm demanding that I want to see qt by t just being R. So what I'm demanding that this being R, plus of course there are subleading terms. Then if I look for a problem where I say that Qt, the leading behavior is this, then that probability has this large deviation form. Okay? For phi. So additivity conjecture does not say much about the form here. You could have some problems where there is still a large deviation form of this kind, but this additivity conjecture does not work. Okay? Additivity conjecture is just a way to get this result. Okay? So there could, yeah. Okay. Okay, so let me say this one more. So you could have first a problem, which is, let's say this one. Okay? And I demand that at large time, I claim that at large time, of course, there would be a part which is scaling with time, and there's a subdating part. And the claim is that there is this large deviation form. Okay? Then how does one calculate this phi function? Okay? So for that, one would formulate a variational problem. Okay? Ideally, one has to just solve this optimal set of equations to get this phi. Okay? It turns out that for this particular problem, the profile that comes is flat, like it doesn't change with time. So that I haven't shown. It's a kind of a conjecture that for any general f function, which is the force, the conjecture is that the optimal profile is time independent, which is a conjecture because I haven't shown it. Okay? If I use that, then I easily get this phi function. You will see that when I'm talking about systems with this interacting particle systems, I would look at an observable, which is a net flow of particles. Okay? There, the large deviation form would apply for a large class of systems. But there's class of systems where this additivity principle or conjecture would work, and you would get this large division form. But there is another class of systems where the additivity conjecture would not work, but you still have a similar large division form. And one just have to calculate the phi function then by solving more rigorously and with more details. So you are absolutely right. That's where the name additivity comes, that you're kind of dividing the system into many parts, and at the end, the large deviation function is sum of large. That's where the original it came, but that idea is equivalent to this assumption that the optimal profile is time independent. Okay? So indeed, for one example that I showed, but that does not exclude. Yes. Right. Okay. So is everything clear so far? Okay. Okay. So I'm now really going to enter the real problems now, which are these systems with many degrees of freedom. Okay. 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 So I'm now going to study systems . Okay, so what kind of systems I have in mind? Let's say you have a system with many particles, and there is a constant, let's say, field, which is driving the system. Okay? Or I have this standard examples that I couple systems with two different baths. So it could be either particle baths or temperature baths, and you have this many degrees of freedom, or the particles which is carrying the number of particles or the energy. Okay. Then I have this other examples, which is Sriram is talking about, which is this active particles. Okay. And I could also think about systems where I started with a box with half of the system with some density rho A, other system is rho B, and I'm looking at evolution. And the kind of things that I'm interested in is to look at the statistics of the slow modes in these systems. Okay? So essentially what I would like to know, that if I look at some coarse-grained density profile of these particles, what are their, let's say, average behavior of that? What are their correlations? And in general, what would be, let's say, the full probability distribution? You can actually ask even at time. And then there would be some kind of large deviation form. Okay? I'm not specifying what is the parameter here, really, but I'm expecting some kind of form like this. Okay? So I want to know these kind of statistics, and I would also like to add that at the very future, we would like to see how does phase transitions would appear in this kind of systems. Are there spontaneous symmetry breaking? So essentially what we are interested in is the collective behavior in these kind of systems with many degrees of freedom. And particularly I'm interested in the systems where they are outside equilibrium, because we still don't have equilibrium statistical thermodynamics equivalent of that for non-equilibrium systems. Okay? Okay, so for that, the starting point is a coarse-grained description of all these kind of systems. And this coarse-grained description is called fluctuating hydrodynamics. Okay. So Sriram will probably also talk about it today. And he will give you some references, but let me give 3 references for this topic, which are more from the rigorous mathematical point of view. And if you like this kind of approach, then you may like these 3 references. One is a book by Kipnis and Nandim, and it's called Scaling Limits of interacting particles, scaling limits of interacting particles. The second is a very famous book by Herbert Spohn, and it's called Large-Scale Dynamics of Interacting Particles. And the third is a long article. It's by Yannick Joel Lebowitz and Spohn. It's in 1996 in J-Stat is 83, page number 385. Okay? Okay, so for my discussion about fluctuating hydrodynamics, I will restrict myself to one-dimensional systems. Okay? One could talk about even generalize this to higher dimensions, and I will mostly talk about systems which are diffusive. Okay? So what do I mean by that? So I'll also describe most of the systems in terms of particle language, but you can generalize this to energy transport or any other kind of systems, or systems of other fields which are evolving. Okay? So I'll restrict myself to studying systems which are diffusive. What do I mean by that? So let's keep this in mind, that if I have the system, and if I couple with, let's say we couple with 2 chemical potentials, or baths with, let's say, 2 different densities. So let's take with the density picture first. Then I'm looking at the systems where the diffusion is the main transport mechanism. And one quantity which reflects that is that if I look at the net flow of particles, okay, up to time t, this would go as rho T by L, rho A minus rho B. So this, you know, is called Fick's law. There is an equivalence in the transport of energy, and that is called Fourier's law. Now, you all probably know that in one dimension, you have many systems where these things are not followed, and it's a active research area to derive these kind of laws, starting from Hamiltonian dynamics of microscopic systems. Okay? And those systems would be called anomalous systems with anomalous transport. So this is third one, which I will not cover. Where essentially the idea was that here the dependence on the system size in the anomalous transport would not be at 1 over L, but 1 over L to the power some power. Okay? And you could study more about this in a really nice review article by Abhishek. So it's in Advances in Physics, 2008. Okay, and it's called Heat Transport in Low Dimensional Systems. Okay, so for my discussion, I will only restrict to the systems which follows Fick's law. Okay. Okay. So what kind of theoretical models I have in mind? So in order to get this kind of diffusive behavior, essentially one would need is to have some kind of stochasticity in the bulk microscopic degrees of freedom. Okay, so you need to some kind of couple a heat bath to in the bulk. Okay? This is roughly the picture. So what kind of systems I have in mind? So let's say a simple would be I have many interacting particles which is following Langevin equations. Okay, I could have xi dot, then let's say, and then they are also interacting with some interaction potential, and then there is stochastic norm. So there are many particles, each following a Langevin equation, okay, and then they're also interacting. So this is one kind of theoretical models one could think of. The other kind of models which are quite favorite in this community are the lattice models. And these are kind of cooked up models because these are little simpler to study them exactly. Okay? So these are lattice models. So typically you would think that there's a system, the lattice, and then coupled with, let's say, two reservoirs, rho A, rho B. And then there are particles which are hopping from one side to the other, or maybe far sides, okay? And every time they're jumping with certain stochastic rates. Okay? So few of the famous examples in this type of models are exclusion processes. You can look at them in this article by Derrida in J.Stat. Nick. There are also models like zero-range process or even Ising model on a lattice. Yeah. Okay, so these are the kind of models that you want to study, and there are also another model which of heat conduction is called KMP model. Okay? And you can look at it in the first paper is in J.Stat. phase 2765, 1982. So these are the kind of problems I have in mind, and we want to study the transport properties, the density fluctuations, and others. Yeah. So it's named after the three authors. It's called Kipnis, Macchioro, and Presutti. These are the three authors. Okay. Okay, so let's just start more of the analysis now. Okay, so the starting point is to write down some kind of dynamical equation, which is like a Langevin equation, for a coarse-grained field, like density field, of these kind of systems. Okay, so most of the cases, I'll have this picture in mind, that if I take the system and couple with two reservoirs, rho A and rho B, okay, then I have the fixed law part, which is Q T divided by T. This goes as T of rho divided by L and rho A minus rho B. Okay? Where the system length L is large and also time is large. Okay? The second property is that if I make the two reservoirs at the same density, then the system is in equilibrium. Then the fluctuations of this current, one could write as so rho, yeah, in general it's a rho A, rho B. But I'm now looking at the example where L is very large, okay, and rho A, rho B are not so different. So rho, so D would essentially becomes D of rho, where rho A, rho B are roughly close to this rho. So it's like the average between rho A and rho B. Okay, the second one is, so this is more in the non-equilibrium state. The second property that I would need is the case where it's in equilibrium. That's where I just couple with the same density, let's say rho A and rho B equal to rho. And then the fluctuations are time equal to sigma of rho by L. So these are, of course, the leading behaviors in the large L and large T limit. Okay? I'm sorry. So this is, so I need these two transport coefficients, sigma and D. And these two are actually related to each other by this Kubo's fluctuation response relation. Okay. Okay. I'm coming to that. Okay. So now, given this picture, okay, I want to go to a coarse-grained description of the evolving density profile. Okay. So here, I'm in the equilibrium case. So I'm taking the system, coupling with the equal density reservoirs, and I'm measuring, sorry, so this should be, of course, capital T. Should be more careful. So I'm now measuring what's the net flow of current, okay, net flow of particles. That quantity is Q of T, and I'm looking at the Q square T average minus QT whole square average, okay? QT average whole square. So this is the variance of this net flow of particles, and this follows this law. And one could actually relate from this to this law by this Kubo's fluctuation dissipation relation. Okay, so it's not, they're not totally arbitrary. Okay, so now the picture that I have in mind is to look at a coarse-grained description of these density profiles in the system. So this is the fluctuating hydrodynamic description. So I will not be very mathematically rigorous at this stage, but I'll like to give them more intuitive picture what's happening here. So I'm considering the system, let's say, into small coarse-grained boxes. I have each a small L, and they're much, much larger than the fast degrees, the correlation length of some fast degrees of freedom. Something very similar to what Sriram has talked, that there is a separation between a slow modes and the fast modes. So I'm considering coarse-grained boxes, each of size, which are much larger than the correlation of these fast modes. Okay? Then one could, just looking at this, one could write down, so x and t is my position and time coordinate, and j is my current. So j is, so this would have been my j. Okay. So this would then have a part which will be like a fixed law. Okay. So this is just roughly saying that if I consider this box, then the net kind of energy flow that's passing through would just be the difference between the density here, this box, and this box. So when I'm writing this, I'm always keeping in mind that I'm not looking at the fast variations of this currents. I'm looking at the slow part of this current. Okay? So this would, you can understand from there. The other part is the fluctuations. Okay? The fluctuations part is right at x of t. And this I could infer from here. Okay? And the claim is, if I look at any time, at any position, this should be 0, because it is almost like if the density difference is very small, so then the average, sorry. Yes, I will later. I mean, I will at the end. So this is xi. Ah, right. Okay, so let's keep there and let's do this. Okay. So I'm going a bit slow because at the beginning you need to understand what's going on, and then I will get into all the algebras later. This would be simply rho okay, so what does it mean? It means that if I look at the fluctuations of current at two different boxes, they are uncorrelated. So we are at a time scale much larger, and also system length much larger than the correlation of the fast degrees of freedom. And the noise is essentially coming due to these fast degrees of freedom, which I'm assuming that they are uncorrelated. And I'm also assuming that locally, if I look at the system, they locally are in equilibrium almost. Okay? So that's where this sigma comes. You can actually see that this description is equivalent to this description, okay, by simply defining this way the total current. Okay, so Q T zero to L dt from 0 to t wiggle, and J of x t. So this is like the average net flow of particles in this box. And then starting from here, okay, you can get back these two relations. Okay? So this is just to tell you that these two are equivalent. So this was roughly the picture that we are now describing a slowly evolving density field, okay, and there is a current field. And I'm interested in the statistical properties of these slow modes. Okay? And the large deviation function when I'm interested in are the statistics of these slow modes. So here writing, while I wrote, I kind of imagined that the x and t I'm always considering beyond a certain coarse grain length. Okay? So one could now write down these things in a coarse grain rescale variable where you don't have to keep this picture anymore in mind. Okay? So let's just write down what is this coarse grain picture. So what I'm going to do now, that I'm going to define a rescale space variable. Okay? I'm rescaling by the box size. I'm also defining the diffusive scaling of the time. Then the point is that if I now look at this quantity, then the slow modes would be captured in this rescaled density variable. And of course, there are subleading corrections, which I'm ignoring because I'm considering small l to be very, very large. Okay? One can do a similar picture for the current also. Because now the current we know kind of scales as 1 over system length. So my rescaled current that I will look at will be now T. And of course, there are subleading corrections, which I will ignore again. Okay? So now the whole description will be in terms of this coarse-grained density and current variables. And this is the statistics that I'm going to study. Okay? Sorry? J. Yes? Oh, so what I said that this is the current of the slow variable part of the actual current. Then I'm looking at the leading behavior of those. Okay? But I know that my current actually decays as 1 over L with the system size for these diffusive systems. So if I want to define something which is not depending on small l, I'll just take it as 1 over small l. So this is the leading behavior. And the coefficient of 1 over small l is my current. And one more reason is that you can actually write down now a continuity equation between these two. So you could have started with, in terms of these slow modes, your result, the continuity equation would have looked like minus del x j of xt. And if you now write in terms of rescale variables, this would simply be q small x t into minus del x j xt. With this scaling, you will find that this becomes independent of small l. And what happens to this current from this behavior? You can easily convince yourself that the equation for the current would now simply becomes d of q small xt del x q small xt plus here, when I'm writing, it would have been, let's first write this part still like this. Okay? So if I had started from this equation, I use these two scaling behaviors, I'd get an equation like this, where the small l are now plugged in here. So I'm just going to define now this quantity as eta small xt. Then very easily you could see, convince yourself that from here I'd get that eta small xt average is 0, eta small xt, eta y t prime as 1 over small l, then q of x at t, then there are delta functions. Now the important part is this one. This 1 over small l. See that now when I'm looking at the evolution equation of this rescale current and density, which is the coarse-grained current and density, they're evolving roughly almost following the Langevin equation. So the additional part that comes, so one part is current is here, the other is this continuity equation. So the total evolution is dominated by, described by this equation, where the current is given by this. And you could already see that the noise part has 1 over small l in it. So this is like the Langevin equation, where this entire part played the role by epsilon. So here you already see, within the fluctuating hydrodynamic description, which is to describe this coarse-grained evolution, I'm already in the weak noise limit. Now you could quite simply see that this is essentially a stochastic differential equation. If I want to study now the properties of the current or the density, I could again formulate an action formulation, very similar as the Langevar equation case, in the small noise limit. And that's how, using again the minimal action principle, I'll calculate the large deviation function. So this is the picture. So this picture is nothing new. This has been there for a couple of decades, and it has played a big role in studying statistical properties of interacting particle systems. The new part, which we call as MFT, is this action formulation. Okay? So I'll now go into the action formulation. So just to tell you that this picture is not really arbitrary, and one could, for certain microscopic models, one could really derive this picture. Okay? So one is, I will leave as a reference. So one was first proved. No, small will stay. Okay? So the idea is that when I'm defining the statistical properties, I'm defining the properties of slow modes. What defines my slow modes is I'm looking at fluctuations which are bigger than this coarse-grained box. And if I choose sufficiently large enough coarse-grained box, then I will get some large deviation form. And in the large deviation form, then the prefactor that came as 1 over epsilon will be played by this small l. Okay? That in most of the cases, I will consider small l as the total system size capital L, because that would not change anything. Okay? Not, yeah, so one, if you take L much, much larger than the system size. So if I had a system size, let's say rho A, rho B, and I take small l to be much, much larger, that would not make any sense. I could take small l to be as big as the system size itself. That would only describe fluctuations which are of the order of, so if I take d small x, it is of the order of L times d capital X. So, okay, so you can consider infinitely large system size, okay? And then for essentially, in order to describe this slow modes, okay, this definition of slow modes comes that I'm looking at fluctuations which are at the scale bigger than this small l. Okay, so I'm looking at things which are varying very smoothly. Even in an infinite system size, I could look at fluctuations beyond a certain coarse-grained scale. Okay? And the L, small l, doesn't have to be infinity. No, it would not go, because that's the small l will play the part as 1 over epsilon that appears in the large deviation function. So it just says, if I'm trying to look at fluctuations which are of the order of this small l, it would be exponentially rare as this small l, right? Okay, so that's what the large parameter is playing. Yes, so if you do it carefully, that's everything fits in and you can do that. No, but the current fluctuations, you would see that at the end, in the diffusive system, the cumulant scale as 1 over capital L. Right, so I could consider, so small l in those systems, you see small l I could consider as replaced by capital L. So I'm taking small l to be very, think about if an infinite system size, yeah. So when I'm saying that I'm not, okay, so this may be a bit a confusing picture, but what I'm trying to say that when I'm looking at, when I'm setting small l as capital L, all I mean is that I'm looking at fluctuations in the box which is of the order of capital L. So it's like, let's say, 0.001 capital L. Okay, so it's just on the scale of capital L, not this. So direct, yeah, direct, I mean, you can go to a variable where this is like I small l by capital L, as in the first lecture I said. Okay? Right, so the strength of the noise will decay as 1 over square root of L. Okay? And this is somewhere related to the simple picture that I'm looking at fluctuations which are uncorrelated. Then from center limit theorem, you just see that its noise goes as 1 over square root of L. Okay? But that's exactly what I'm going to come and talk about. Okay? Yeah, you will see that the minimal action, it's the same picture. The 1 over small l, So think about systems on infinite system size, then I don't have a capital L. And then I could think about small l as being a coarse-grained box. The small l only describes this, what is the definition of these slow modes. Okay, so just to make this point which more rigorous, that I'm just going to give this two references. The point is that these are not so hand-waving. You can actually, there are microscopic models where you can really prove these things explicitly. So I'm just going to give this two examples. I'm not going to prove anything, I'm just going to give the references. So one, you already know this thing. There's something called Dean's equation, which describes a coarse-grained description of interacting many Langevin equation. I'm going to write it. So, okay, let's see. Where did I misplace it? So, okay, I have misplaced some parts. Let me give this reference then later. I'm disarranged my notes. But this is a paper by David B. It's about interacting many Langevin equations, the one that I wrote at the beginning. The second one is for, let's say you have a lattice model where there are particles which is jumping, and let's say they are non-interacting particles, or it could be a model of exclusion process. So this is called symmetric exclusion process. Okay, where the rule is that the particle jumps only to its neighboring sites with equal probability, so either of the neighboring sites, with the condition that the destination site is empty. Okay? So for this model, also one could prove this fluctuating hydrodynamic equation. So this equation is called fluctuating hydrodynamic equation. So these two equations. And for this, I have the reference because it's my paper. If you want to look at the fluctuations, 2016. There's also a version which was much earlier by the original guys who first came up with this MFT description, which was by, I'll give this also reference, I don't remember very well, but it's by Giornalasinio et al. And it was in J. Statphase, 2002. Okay, even there is a proof there. Okay, so now let me just kind of summarize this picture, what I have told you so far. And from then onwards, I'll move on to this action formulation. So you could already see that this is essentially an analysis of stochastic differential equations, and which is very similar as the Langevin equation. And I could, in a very similar way, go to the action formulation. Okay. So let me just repeat this part again. So far, I have this coarse-grained description, which is fluctuating hydrodynamics. I have this coarse-grained density profile in the coarse-grained space and time scale. So here is the continuity relation. And the current is given by, the first part is by Fick's law. And there is a fluctuating part where on an average, the noise is 0, and the covariance will write as sigma of Q divided by L. So these are, of course, a function of time, and they are delta correlated for both space and time. So this is the whole picture, starting point. And we have this picture in mind. So that we're assuming that locally the system satisfies some local equilibrium. Okay, so these fluctuations of the noise comes from the fluctuations of the equilibrium. So one would, in this whole description, you could first see that all the microscopic details of the problem have just embedded in this coarse grained description in terms of these two transport coefficients. If I have a microscopic model, I only have to determine these two transport coefficients. And from there onwards, I just start from here. And then I try to calculate all the statistical properties of this fluctuating field. Okay? It is QXT. So this is the multiplicative term. Okay? So how does one calculate these kind of transport coefficients? Okay. Typically, one could start from this definition here. Right? So I know how from here one could define the current here. So you see that this D is exactly the same as the D appeared here. So the rho dependence of D, you can simply calculate by coupling the system to two different particle reservoirs and measure the net flow of current and net flow of particles, and this D one could measure. The second one was from this fluctuation relation, fluctuations of current, and this would have given you the second transport coefficient. Okay? So this one way to do it. The second is sometimes in the lattice models, it's quite simple to calculate this term D, which we would call as diffusivity. So let me give the name. This will be called as diffusivity, because it kind of describes, if I have a density fluctuation, how the spread is diffusing. Or this will be called as mobility. Okay. So how does one calculate typically from the microscopic models? It's a simple relation. So it only describes the fluctuations of the current. Okay? The mobility describes that if I have a system in equilibrium and I look at the net flow of particles and I look at its variance of the current. This is described by this formula in the diffusive systems, and this defines your mobility. I'm just now saying that, of course, one way to measure these microscopic transport coefficients is by using these two formulas. Another approach is that using this formula, which I'll prove later on. Where F rho is the canonical free energy. 1 over L log Z L times rho times L. So this is the total number of particles. Okay. I'll derive this relation. Okay. Okay. So what one typically does, often in many systems, calculation of this diffusivity is quite easy. Okay. So just simple example that if you take a system of non-interacting particles, okay, jumping on this lattice, then one could very easily show. So you'd see that if I want to look at the current between site I and I plus 1, so the average current would simply be, so the net probability for the particles to go from site I to I plus 1, it would simply be proportional the number of particles in that side minus the number of particles, so the flow that came from I plus 1 to I, so that is proportional to average of n plus 1. Okay? And now, if I want to define this, what is this diffusivity, I want to write it in this formula form, and it's very simple to calculate in this problem. Rho A, B. So Ni's are the number of particles at site I, which is a fluctuating quantity. And I'm now going to define at site I, what's the net flow of particles from I to I plus 1 up to time t. So I'm going to calculate this coefficient d for this problem and see that it's very simple. For that, I just need to do dt from 0 to capital T, average of ji at t. Then if I just write down, so then there is a sum over I. If you now write down this here, you will see that there is a telescopic cancellation, and you will only get that this is simply this, everything inside would be simply n at 0, n average at 0 minus n average at site L, which are nothing but, this is simply rho A, this becomes rho B, which are time independent. So you would get T rho A minus rho B. And if I want to have it this formula, so I'm looking at the quantity now, Q of T average, which would be then simply divided by total number of sites. Okay, so there would be 1 over L. Then you would very easily see now, this divided by T is 1 over L rho A minus rho B. So D is 1. Just looking at this formula. So this is just a simple exercise to show you that one could calculate D sometimes quite easily. Then just use this formula. And for models, many simple models, this F is very easy to calculate. So for example, in this non-interacting particle case, it's very simple because if my system is in equilibrium, so these two are the same density, then all configurations are equally probable. Okay, so let me just remind the thing. So I now want to calculate the sigma for this problem, given D is 1 by this relation, and I only need to calculate F. Okay? So for F, see, I have to be in a system which is in a canonical ensemble. I look at this version, I put it, the system, in the canonical, so no particle is flowing. So I have a certain number of particles which are jumping around. And its system is coupled to a heat path. Okay? So for that, you can very easily show that all configurations are equally probable. So if I look at the partition function, for n number of particles in this system, the system length L, it is nothing but this one. Okay? Then by using Stirling's approximation, you will very easily end up, so rho is equal to n over L, equal to 1 over L log of Z. And using Stirling's approximation, you will get this is equal to rho log rho minus rho. Okay. Then if I take F double prime of rho, this would be simply 1 over rho. Okay? So then, if I use this relation, it tells me twice D is 1, this is 1, with respect to the density. So it's only a function of the density. So I'm just taking double derivative of this expression. It will give me 1 over rho, divided by sigma rho. This is F double prime of rho, 1 over rho. I'm sorry. So, yeah, it's okay. So this will tell me sigma rho is equal to twice rho. I'm running really slow. Okay, so for non-interacting particles, then D is 1, sigma is twice rho. Sorry? Right, so I'm assuming so far KBT is 1. I'm just setting, but otherwise you can of course put it a KBT. Yeah. Right. Right, so what I'm doing is, so far, is that there is a stochasticity when the particles are jumping. Right? And that stochasticity defines the temperature. Exactly, so there's an effective in the particle case, there's an effective temperature. Right, in the bulk, it satisfies detail balance. So far, in all these cases, so these are systems which are made non-equilibrium by the boundary conditions. Precisely. So far, I'm looking at only these kind of systems which are at the bulk satisfies detail balance, but they are brought to non-equilibrium by coupling with two different reservoirs. Okay? And the developed analysis for the cases where there is a bulk drive is still very difficult to do and has not been fully developed yet. Okay, so now, after all these discussions, let's really go to the action formulation. Okay. So you have to keep in mind now this following property, that all the microscopic details in this picture are now embedded in this two transport coefficient D and sigma. In this coarse-grained description, the whole evolution of the coarse-grained fields are captured in just these equations. So this and this equation with this noise terms. And now I want to look at the flux. Sigma rho is equal to 2 rho. So for non-interacting particles, sigma rho is 2 rho. So let me give just one more example without calculations. So I told you that there is a symmetric exclusion process, which I described. So for that, if I look at SEP, for that, D of rho is again 1, and sigma of rho is twice rho 1 minus 1. Okay, so now I'm going into the action formulation. I don't know if there is any physical significance of this, but so this is a relation between two transport coefficients. Okay? It's kind of a picture of Kubo's fluctuation dissipation relation, which just says, if you think about this relation, D is like the response function. It's like you are perturbing the system. If it is roughly in equilibrium, then you are making slight change in the parameters, which is like changing the densities. Yeah. So this is like the response function. This is a fluctuation when the system is in equilibrium. And you know in thermodynamics already you could relate energy fluctuations with the specific heat. Okay? So specific heat like the response function, you increase temperature, and that's related to the energy fluctuation. So this is kind of a result of that kind. Okay, but within the action formulation, I'll tell you how to derive this. Okay? So that would be like an exercise for this variational problem. So now I should really get into the action formulation. I spent too much time in this fluctuating hydrodynamics. True. True, you can definitely derive that way. I'm going to derive it because that would be an exercise of an action formulation. Okay, so only thing that you have to keep in mind, now we are in the coarse-grained description. Most of the microscopic details are in these functions D and sigma. So if I am given a particular model, I just need to calculate D and sigma, okay, and then start with this equation. Okay? So that's where the generality comes. So now I'm going to enter in the variational formulation. Okay. So now again, we are going to think about, similar to the Langevin equation case, an evolution of this density profiles, both density and current. So if I try to just schematically describe a path of this density and current profile, which is evolving, doing something like this. Okay? And all I want to know now, what is the probability of seeing a particular trajectory or the history of this system, okay? Of this evolution of density and current profile. So this is like a trajectory. And what I want to know is the probability of seeing a particular density profile and the current profile. Now you could very easily convince yourself that this would be, so now I have this picture, okay, minus small l. I'm looking at time evolution, let's say from 0 to capital T. Then dx, 0 to, I don't put so right now. J plus d q now this is very obvious, right? Because the fluctuations are due to the noise part. So what is going in the exponential, you see the noise has only the average is 0, the variance is delta correlated, and higher cumulants are 0, so it's like a Gaussian. Okay? So essentially the probability of each trajectory is the probability that of the noise. Okay? So the probability of the noise would have been just e to the power. So let's just write down here. The probability would have been, I've looked at et dx eta xt whole square. Okay? This would have been 1, and the variant in the denominator it would have been twice sigma q. Okay? And from there onwards, I just rewrote this, and you would see that from that equation, your probability of each trajectory would simply be this. So maybe I missed some small l, but right now I'm not going to quibble much about that. Okay. Right, so there would be a Jacobian. That's why I did the exercise in the second lecture, that the Jacobian part would not scale with this small l parameter. So when I'm looking at, this large L parameter, so all those terms that's coming due to the Jacobian would not contribute. So all those confusions about Ito-Stathnovich would not appear here as long as I'm looking at large L behavior. Okay? True, you're absolutely right. So in addition, there is another condition. So this part came simply from this equation. I have this part also to take care of. So for that, I'll simply I'll just write them as dq plus del x of j, the delta function. Okay. Good. Okay. So now, let's say I want to write down the problem. So now let's look at one problem now. So now we are all set, and now we will solve exercises after exercises. Okay. So now I want to look at, let's say, I only want to look at the density profile. So I want to look at the final point, xt, being r of x. At the initial, I start at qx at 0, being, let's say, rho of x. So this rho is not the one that I used before. Okay. So this profile, then, so I'm doing r of x, rho of x. It simply be now the path integral over q and j with this action. So let me just still repeat it again. Or maybe I don't need to repeat it. So this part. Okay? With all the fields that started, the qx0 started at rho of x, qx at t goes as r of x. So I'm looking at now all fields which only for the density they're constrained, that initially it's rho x, finally it's at rx. Now, what I'm going to do, because I'm interested only in the statistics of the density for this problem, I'm just going to integrate over the J. And how does one do that? Okay? And you will see that there is a Hamiltonian picture which will emerge from this simple exercise. Okay? So, what I do now, so I leave this part. Okay? So let me still rewrite. I'm just going to rewrite this part. L dt 0 to t dx j plus d del x rho del xq whole square by sigma. Now what I'm going to do, I'll just represent this as a Fourier integral of representation of the delta function. That's simply done. So now these are, remember these are fields. So this will introduce that conjugate variable in the Hamiltonian picture that appears. So this is the momentum variable. You will see that it will immediately come. So this I'm just going to now write as minus small l. So this is how I'm just going to write it. P del tq plus del x of j. Okay. Now, the point to note is that, see, the whole term in the exponential are quadratic in the current, it's j. You can do a Gaussian integration. All of you know how to do Gaussian integration. If you just do the Gaussian integration, okay, then you would end up with path integral over q and p variable. So p is some arbitrary field. I'm not constraining anything. I'm only doing Gaussian integration over the j variable. Okay. Then if you do the Gaussian integral, you will end up very easily in this following form. So let me just write that. And you will get this Hamiltonian picture. There are many other ways of deriving this final form of the action, like the one like Martin C. Gero's that I mentioned before. And this is just one way of arriving there. So finally, the formula would be this. So Rx, rho of x. This would be now the path integral over now only the p variable and the q variable. And all the terms in the exponent I'll write as action of p, q. Okay, let me just finish writing, then I'll come back. This you will find that it has a Lagrangian picture. So I'm going to write it as this. P q dot minus h p q. So this is the Hamiltonian. And you will find that the Hamiltonian PQ is given by this form. This is like the kinetic energy part, and this is like a effective potential part. Okay, so this is the Hamiltonian. It should be small. Here there should be small j. Yeah. So all now are all. Yeah. So now all of I'm already in the coarse grain variable. So j is always small. Yeah. So yeah. So all of them are small x. Sorry, it's my bad handwriting. And so now I'm only in the small x, small t variables, small j variables in the coarse grain picture. So this would be your action. Okay. So now let's just solve the one problem that I did for the Langevin equation case, which is to derive the stationary probability distribution. Okay. In a very similar way that we derived for the Langevin equation case using time reversible property. You all remember what we did. Okay. You will see that very simply the results will come up. So now what I'm going to do, I have this following picture in mind. Yeah. Yeah. Yes. Okay. So now I have this picture in mind. I'm taking the system, coupling at the same density at the two end. My total system size is small l. Okay. And I want to look at what is the probability distribution of seeing a density fluctuation Q of x. This, in the first lecture, I told you that one could derive from equilibrium statistical mechanics using the partition function calculation, that this has the following large deviation form. So this is a function now. So, I'm sorry, let's just change this notation. This is what I'll be using. Okay? And I gave you the expression the first day. I left it as an exercise last time. This was the x. The x now goes from 0 to 1 because I'm in the scale variable. This was small f r of x minus small f rho minus f prime of rho r of x minus rho. This we derive, I left it as an exercise, but this one could derive from equilibrium stat mech. All I'm going to do today is to use this action formulation, derive the same result, to be sure that now everything is consistent. Okay, so now, now the same picture holds now. So what I'm doing now, I have this probability distribution. My initial, so I have the same picture that I start at minus infinity, time minus infinity. So I want to, at time minus infinity, this is the most probable profile, which is the average density is rho. I want at time 0, this to be at Rx. I'm looking at now all possible evolutions with the weighted probability of each path, and the weight of each path comes from this action. Action is given by this. And again, in the large, small limit, this large L limit, this is dominated by the saddle point. So all you have to show now is that phi of R of x simply the S min of this Q of t, P of t. So there is a optimal path which starts at this rho x, so it starts at rho, ends at R of x, which started at t minus infinity, and here it's 0. So there are many such paths, and one of the paths which is dominant comes from the saddle point and gives me my large deviation function. Okay? So it's not a surprise that the equation satisfied by this minimal action path will follow Hamilton's equation. Okay? Because this is the Hamiltonian term. Action has this form. Okay? So let me just write down how does equations now look like. And I'm going to use that same property of time reversibility. And you will see that the answer will come. So far, you see, I just put L by hand. Okay, I'm not assuming. So if it does not work, the P would be something different. Exactly. Yeah. So from examples I'm doing, but because I already know, but while I'm doing this, I'm not making any assumption. I'm just defining a field which is P, and I'm putting a L. If this thing does not work, I will see it when I'm doing an exercise. Okay? Right, that's also true. Exactly, that's also true that by writing this way, I'm getting the small l as a prefactor of the action, and then I can do the saddle point. That's precisely, it's a better answer. Okay. There's some strange thing that I did, but which I will let you to figure out there. And there is an answer for that too. But okay, so now all I have to do is to find the optimal path, which is the path of least action. Okay? And the path of least action will satisfy Hamilton's equation. So now you have to keep in mind we are doing everything in terms of fields, unlike in the Langevin case. This will be a functional derivative. The other part, P minus del H del Q of xt. Okay. And how does this equation look like? So if you start from this given expression of the Hamiltonian, take this functional derivative, which I believe everyone knows how to do, you'll get an equation. Q dot minus del x dq del x cubed minus del x q del x. This equation will give you p dot plus q del double derivative p equal to minus sigma prime of q divided by 2 del x p whole square. So this is a coupled partial differential equation. It's very, in general, it's very difficult to solve. So I have these two equations, and you know I need two boundary conditions. So one condition comes from this property that at initial and final time, I want to see a specific density profile. So let me just write down. So one condition is that at minus infinity, I want it to be rho constant. Another one is at time 0, I want it to be at profile r of x. I have two more conditions. One is that at the boundary, because I'm fixing the densities, the r has to be exactly rho. The boundary, so at boundary, so not just r, even when this profile is changing, it has to be kept fixed at the two end. So at any time, if I look at the left boundary, the density field, it has to be rho. And also on the right boundary, which is now in this reduced coordinate, is at 1. Okay, I'll take maybe 10 minutes to take it. So this is 1. The second will come. I'll give you justification again, why. So x, I'm in the rescale variable, right? So I had gone, the small x is capital X divided by L. The right boundary is 1. So first boundary condition is obvious. Where does this come from? So you have to realize how we got the p term. The p term came because when you derive the action, I had this delta function, right? So j plus, so del xj was del t rho. Now if you think about, so in the bulk, the particle number is conserved, right? So because in the bulk, the nowhere particle is vanishing. So this condition is appropriate in the bulk. But if I look at the boundary, there it is not conserved in the sense the particle is coming from the bath. So I'm not going to put this condition at the boundary. So that kind of gives a justification why one would need this to be 0, because P came because I wrote delta function as a Fourier transform. So it only says it's kind of related to the fact that I'm not putting this continuity condition at the boundary. Okay, so now given this, I need to just solve this. Okay, how does one do that? So in general, it's difficult to solve. I'm now just going to use this time reversibility property. I think so. Yeah, I think so. It would also give that. So now I just want to solve this equation. I'm going to use now this time reversibility. Okay, so what does time reversibility tells me? You see, again, you should look at this equation. Okay? And if you remember that if I started with this fluctuating hydrodynamics equation, which was here, if I plug the formula of J here, all I will get, if I put it here, I'll get del x d of q, del x of q, then minus del x of eta, right? If you take this term and compare with this equation, you see that this term almost plays the role of eta. So the physical picture is that this conjugate variable P is due to this correlated noise history that will give me this final position. Okay? Okay. Now, I have to just think about this relaxation, the two different paths, the forward path and a backwards time reverse path. So all I'm now looking at, there's two pictures. So I have this, so it's just a schematic. So now we don't have a potential really. So I have one position, where there is a most likely density profile, which is rho. And I'm asking, what's the probability of seeing another density profile, which is less likely? Okay? So what I'm asking now, starting here, I want to go uphill. So all these solution of this equation will tell me what is the most likely path that will contribute if I want to go uphill. But I could think about the reverse problem. I could have started at Rx, at minus infinity, and I want to relax at the final time here. So for that, just like in the Langevin equation, that would be dominated by the noiseless solution. Okay? So if I use that property, then you would immediately realize that using that time reversibility, all I know that I will find out that this equation, the Q, will just satisfy this equation. Very similar as in the Langevin equation case. So all what I did, if I had written this thing in terms of the relaxation process, the reverse one, time reversed one, I would have followed just this noiseless equation. And I'm writing by changing the time to minus t, I'm getting back the forward process. So that would give me this one. So I already know this. Now, how could one get this equation from this equation? Okay? So the only thing that I need to is to change the sign here. You would immediately realize by looking at this equation, if I write down now P of xt as simply rho, then Q of xt, then some ds twice ds sigma of s. I take this, so rho here is constant, so if I take a derivative, it will give me this quantity, this 2d at q by sigma q. I put it here, I'll get twice this one, okay, with a minus sign. And then from here, I'll get this. So all I'm saying that if I assume this form for the P and substitute here, it will give me the expected equation that came from the argument of time reversibility. Next thing what I want you to check, if you take this equation, put it in this second formula, you will see that it automatically satisfies this equation. Okay? So essentially then, from this analysis and argument, I see that my least action path is simply given by the solution of this Q, and P is given by this formula in terms of the solution of Q. Now we are almost done. So if I have this too, I only need to calculate this minimal action now. Okay? So we're almost done. So just one more comment that I want to make before I just show this, that you remember in the case of Langevin equation, we have found that for the optimal paths, in this case, the Hamiltonian is 0. Okay? Even in this case, if you put those two solutions and put it in the expression of Hamiltonian, you'll find that it is 0. Okay? So for this problem, H, Q is 0. Now I want to calculate the minimal action. The minimal action now phi of R of x is the S min with P of Q. Now if I look at this formula, H is 0. Okay? I only have this term. So let's just rewrite it. I take the space integration first. It's from 0 to 1 dt from minus infinity to 0. Okay. P times Q dot. Okay. All I need to do is now write down dt Q dot as dq. Then I will have this going from rho to R of x times P. Did I do it correct? So I probably made some mistakes. So let me just repeat it one more time. So maybe the last step that I did is wrong. So please correct it one more time. So I'm rewriting it. So we're almost there. So just hold your patience and we'll be there in just a few lines. I'm writing the same thing again because I just jumped a step. Okay? Right. Exactly. So I'm now going to write that. I'm now just going to write P in terms of Q. Okay. So, right. So P there, I have it in terms of Q, right? So P rho to Q xt ds, and I had twice ds by sigma s, right? Now, I told you in the beginning that there is this relation. So this is double derivative of the free energy. All I'm going to write down now is F double prime of S. Okay? And I take that and put it here. So let's just first write down this. So this would be F prime of Q xt minus F prime of rho. Take that and put it here. So I'm just going to rewrite this part at Q dot F prime at Q minus F at rho. Okay? Now it's very easy to show now. So what I'm going to do now, you just do this time integration. So the first part, let's just do it this way. So this term was simply, I write, so dt Q dot F prime Q. I just write this thing now in terms of Q integral. It becomes dq. Start at rho. I'm at Rx. Minus this part, it's F prime, prime of rho. And I only need to do the integration over Q dot. So this would give me R of x minus rho. Is clear what I did here? I just did this integration. So here, this part and this part separately. Okay? So now we are almost there. So this, you can very easily now see, this is from 0 to 1, f of r minus f of rho minus f prime of rho r minus rho. This is the result we derived from the equilibrium. Okay? Okay, so sorry, I took almost 10 minutes or more today. Okay? So this is one verification we did. So far, whatever we are doing is consistent. Okay? And this is one example of showing you how to apply this variational problem or formulation to solve the properties of large deviation function. Okay? So the next lecture, I will talk about a few other properties like the additivity principle and show you how one could solve using this, calculate large deviation function of current, and I'll also show you how one could get this long-range correlation starting from this kind of analysis. So all we'll do in the next lecture is use this variational formulation. All these long-range correlations and non-local large deviation function will come out of this very similar action minimization problem.